So as we said, we want to separate the sum term and the x to the m outside and only leave the coefficient in the middle. And that is how we arrange from the previous equations. Then we found that the coefficients, we have two different coefficients. One is the am plus 2, the other is the am. So we want to put all the coefficients for the am plus 2 together, all the coefficients for m together. And we also see that for this power series, that in order to make this sum to be 0, the x to the m won't be 0. Then we need to have all the coefficients to be 0 so that this whole term can be 0. That means we have the m plus 2 times m plus 1, a m plus 2 minus m squared plus m minus 2 am equals to 0. Then based on these equations, we can find the relationship between the am plus 2 and the am. Then we can solve our power series general solution, homogeneous solutions. So we have m plus 2 times m plus 1, that is equals to m plus 2 times m minus 1 am. And m plus 2 can cancel out because the smallest number for m is 2, right? Is 0. So this term can be canceled out. Then what we get am plus 2 will be equals to m minus 1, m plus 1 am. So this is the relationship between the coefficients am plus 2 and am. And since there is a two term here, we can separate our power series to be the even part and the odd part. So the sixth step is to trying to try to generate the homogeneous solution using power series. And so what we have here, we have am plus 2 equals to m minus 1 divided by m plus 1 am, right? So for the even part, basically we start as m equals to 0. That is the smallest. Then a2 will be equals to what? A2 will be equals to minus a naught. Okay, a2 will be equals to minus a naught. The second even number is m equals 2, so a4 equals to 1 over 3 a2 will be equals to minus 1 over 3 a naught. M equals to 4, a6 equals to 3 over 5 a4 equals to minus 1 over 5 a naught. Okay, so you can do a8, a10 solved by this relationship, get the relationship with all the even part coefficients as relationship referred to the a naught. Then for the odd part, the smallest number is m equals to 1. So a3 equals to m equals to 1. Okay, m equals to 1. 1 minus 1 equals to 0. So it's 0 times a1. That will be 0. M equals to 3. a5 equals to 2 over 4 a3. But since a3 equals to 0, all the term will be equals to 0. Okay, so m equals to 5, 7, 9, will be all equals to 0 for the odd part. Then our original format of the power series is start with m equals to 0 to infinity am times x to the m power. Then we can separate into the odd part and the even part. So that's right. The odd part is easy, relatively easy. We only have a1 here. So a1 x when m equals to 1. For the even part, we'll start with a naught. So a naught x to the zeroth power will be 1 plus a2 x squared plus a4 x fourth plus a6 x to the 6 plus dot 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 equals to a1x. Let's replace the coefficient always the a naught plus a naught minus a naught x squared minus 1 over 3 a naught x to the fourth minus 1 over 5 a naught x to the 6 plus dot dot dot. Then let's make a naught all come to the a naught to be the coefficient, all the other term put together. So it will be a1x plus a naught times 1 minus x squared minus 1 over 3x fourth minus 1 over 5x 6 minus dot dot dot. Okay. Then let's see, because this is going back to our, very original problem side. This is a second order ODE. And as a second order ODE, this is a homogeneous equation. So we don't have the particular solution part. This is only the homogeneous solutions. Homogeneous solutions, the complete set for a second order ODE will be two linear independent solutions. So do we have two linear independent solutions? We have. The one part will be x, the other part will be this whole series, and the coefficient, and they will linear combine together to be the homogeneous solution. So the constant will be a1 and a naught here. Okay, so we have c1 equals to a naught. That is the constant, and that is combined with the y1, which is the first linear differential, first linear independent solution, which is y1 minus x squared minus 1 over 3 x fourth minus 1 over 5 x6 minus dot dot dot. Then you have c2 equals to a1, y2 equals to x, and you can check whether they are linear dependent or null dependent by Wronski matrices. So this is the complete homogeneous site for this second order ordinary differential equations. Then let's make it a little bit more complicated by giving a boundary value problem for this equation. So let's assume a BVP where the y naught will be equals to 1, y final, which is when x equals to 0.9 equals to 5. So you have c1 at y1 x naught plus c2 y2 x naught equals to y x naught. Okay. Then c1 y1 at x final plus c2 y2 x final will be equals to yx final, because they are linear combined for these solutions. Then you can make a state space representation for these two linear equations, linear algebra equations. So you have y1 x naught, y2 x naught, y1 x final, y2 x final times the coefficient c1, c2 will be equals to yx naught, yx final. Okay. Then when x, so based on this solution format, x naught should be equals to 0, x final should be equals to 0.9. You c1 will be equals to a naught, c2 will be equals to a1. You y1 will be equals to 1 minus x squared minus 1 over 3 x fourth minus 1 over 5 x6 minus dot dot dot. You see y2 will be equals to x. Then what you can do in order to solve these solutions, you at least need to know, okay, all the terms inside these equations, then you can solve, right? So you easily can get what is y2 at x equals to 0, y2 at x equals to final, because that is just equals to x value. But you don't know is when y1 at x final, because that is a power term. So that is an infinity power series term. Y1 at x naught is easy to know because that is just the one, but Y1 at x final is not sure. So you need to do a looping in order to know what is the Y1 xf. Okay, so Y1 xf have to be, has to evaluate infinite series. And here we need a looping structure. Okay, we need a looping structure. And that is what we have been present before. The logic of this incorporating the infinite series into a looping structure, you basically find what is the T1 term, what is the F1 term. So the T1 is the first term, yeah, F1 is the sum of the all the series, but you define the first one, which F1 should be equals to T1. Okay, you figure out the radius, which is Tn plus 1 over Tn, will be equals to, for example, for this term, will be equals to m minus 1, m plus 1, x squared. Okay, so you have to figure out at what kind of range of the x this part can be converged. This part can be converged. Basically means this radius has to be smaller than 1. Okay, the radius has to be smaller than 1. Then after that, basically you can say, okay, at this x range, the power series can be converged. Then we can evaluate what is the y1 term. Okay, then we have this y equals to 1 minus x squared minus 1 over 3 x fourth minus 1 over 5x to the 6th. We can evaluate when this x is in the converged range. So we have y equals to 1 minus x squared minus 1 over 3 x fourth minus 1 over 5 x 6 minus dot dot dot. And you can code this part into the program, and we can evaluate the y1 xf, and we can solve these final equations. Okay.